Hi everyone, I am Ryoichi ISHIMATSU from University of Fukui. Welcome to my presentation. This time I would like to introduce my research topics about electro-generated chemiluminescence, ECL. First, let me compare fluorescence and ECL. Fluorescence is a light emission phenomenon caused by light absorption. Molecule at the ground state can be excited to the excited state by light absorption, and then fluorescence can be seen through the radiative transition, and this is a figure of fluorescence by irradiating UV light. In the case of ECL, instead of light energy, you can excite molecule by applying electrical energy, and then light emission can be seen, which is called ECL. And this is a figure of ECL by applying electrical energy at the electrode. Let's take a look at the ECL mechanism closer here. Here, R stands for fluorescence molecule. When you apply a voltage to the electrodes, you can generate radical anion and cation through the electrochemical oxidation and reduction. These ions diffuse, and when the distance between these ions gets closer, an electron will transfer from here to here, and then excited state will be formed. So after that, you can see ECL. It should be noted that these reactions occur in a liquid state, not in a solid state like organic light emitting diodes or OLEDs. Currently, we are interested in electrochemical properties and photophysical properties of fluorescent molecules, and also electron transfer dynamics of radical ions. Let me show you an application of ECL. ECL is attractive for light-emitting devices, which are liquid state. This is a very nice picture of blue, green, and red color ECL device. The thickness between the electrode was about 5 micrometers. There are several merits, such as that you can fabricate ECL devices easily because they are very simple structure, just a solution between two electrodes. Fabrication cost could be low because the simple structure. However, there are several weaknesses, such as the weak light intensity and short device lifetime. These weaknesses should be improved for practical application. One way to realize a stable ECL system is to use stable radical ions. You can easily check how stable the radical ions are through cyclic voltammetry. This is an illustration of cyclic voltammograms, which are a relationship between the applied voltage and the current flow. In this measurement, voltage will be cycled like this. The blue one is a typical response for stable radical ions, that is the peak current in the backward scan here, is comparable to that of the forward scan here. When the radical ions are unstable, the current response in the backward scan decreases like this way. The red one is a typical response for unstable radical ions. For a multicolor ECL system, we employed several photoluminescence molecules. We studied the electronic structure and photophysical properties, such as the fluorescence spectra of the newly applied molecule, to understand the ECL properties. This photograph is a fluorescence from a molecule, and these photographs are multicolor ECL generated by disc-shaped electrodes. We focused on the electron transfer dynamics, including the rate constant and electron transfer distance. In this slide, I would like to introduce our recent studies on electron transfer distance in ECL. Because the electron transfer process is coupled with diffusion, it is quite difficult to reveal the electron transfer dynamics, such as the electron transfer distance. The electron transfer occurs at a distance between the radical cation, and anion, and after electron transfer, the excited state of a molecule will be formed. But these excited state and ground state will diffuse, and for some molecules, excimer state will be formed. The emission wavelength of the excimer appears at longer wavelengths compared to that of the monomer wavelengths, monomer emission. So the intensity ratio of the monomer and excimer may give an idea of the electron transfer distance. For example, when the distance is long, the monomer emission will be stronger compared to the excimer emission. On the other hand, when the distance is short, monomer emission will be weaker than that of the excimer emission. We use Pyrene, which shows an intense excimer emission. By comparing the ECL intensity of the monomer and excimer emission, we found that the electron transfer distance is about 1 nanometer. We are continuing this kind of research to reveal the electron transfer dynamics further. We are pursuing stable and intense ECL systems. Various phenomena are related to the expression of ECL, and it is very important to understand the electrochemical and photophysical properties of molecules and the electron transfer process of radical ions. We also need to develop new molecules which are related to material chemistry. There are many unknowns in ECL. By performing experiments comprehensively, we will clarify the unknowns in ECL. I think ECL is composed of three main components: electron transfer, electrochemistry, photophysics, and material chemistry. Like RGB color, ECL is based on the three main fields. These fields should be combined and considered to understand the ECL behavior deeply. I think doing ECL experiments is interesting and exciting. I am sure that when you observe ECL for the first time, you will be excited, as many students did. All students, undergraduate students, master course students, and PhD course students are all welcome. I hope to see you in Fukui. Thank you for your listening. Thank you. Bye-bye.